our main topic today is optimization, using derivatives, just like in Calc 1, to find critical points, classifying them as maxes or mins, or maybe neither. Start with a couple examples where you don't have to use derivatives, that you can just think about it. And actually, this first example is at least somewhat similar to the example I did at the beginning of chapter 12. Take f of xy to be the square root of, say, something like 1 minus x squared over 9 minus y squared over 25. I'm interested in optimizing this function, finding its maximum and minimum values. We have to be a bit more careful about domains. When you say find max and min values, what domain are you talking about? If it's not specified, it's the maximum possible domain, the biggest possible subset of the plane on which this function is defined, giving you real outputs. If we allowed for imaginary number outputs, then what's under the square root could be negative, but we're not doing that in this course. So for the domain, we require 1 minus x squared over 9 minus y squared over 25 to be greater than or equal to 0 for the domain. So in other words, this inequality defines the domain, i.e. the domain, you could call it D, is the set of all points in rectangular coordinates satisfying that condition, which could be rewritten as the set of all points satisfying this inequality, x squared over 9 plus y squared over 25 is less than or equal to 1. This is called set builder notation. You read this as the collection or set of all points x, y in the plane, which you could call R2 if you like, satisfying that inequality. Alternatively, that's the set of all points in the plane R2. This funny looking E means in, satisfying this inequality. And if you graph the corresponding equation there, it's an ellipse with x-intercepts at -3 and +3, and y-intercepts at -5 and +5. If you imagine setting this equal to 1, and think about finding x and y-intercepts, if for x-intercepts you'd set y equal to 0 and solve for x, and you get x squared over 9 equals 1. So x is plus or minus 3. And for y-intercepts, you'd set x equal to 0. Solve y squared over 25 equals 1. You get y equals plus or minus 5. And that ellipse is the boundary of the domain. The ellipse is boundary of D. There's a somewhat common notation for the boundary of D that makes it look like a partial derivative of D. So there I'm using the del curvy D symbol, whatever you want to call it, partial derivative symbol, as if I'm taking a partial derivative, but I'm not actually. It's just a special symbol for the boundary of D. There's actually a little bit more meaning behind this than what I'm indicating. But effectively, this is good enough for what we're doing here. That ellipse, and then the interior of the ellipse is also including in D itself. So D itself is the inside of the ellipse, the interior, and the ellipse itself. This is the union of the inside of the ellipse unioned with the ellipse itself, which is this boundary of D. This is the union symbol. It just means combine the sets. This is an example of something called a closed set. You remember closed intervals? Closed interval is an interval written like that, on a number line, it's all the numbers between A and B, including the endpoints. You might think of the endpoints as being the boundary of the interval. Maybe we could even write the boundary of this is the two-element set AB. And we call it closed because it contains those endpoints. If it did not contain the endpoints, we'd call it open, an open interval. It's kind of like the boundary, those endpoints kind of close off the interval. Nothing past them is in it. If we did not include the boundary, the boundary points at A and B, that's an open interval. And, open intervals are a little funny if you think about it. That interval there doesn't have a highest point or a lowest point in it. A is not the lowest point because it's not in the interval. B is not the highest point because it's not in the interval. These subtle points I'm making are really important. As an example, the open interval from 0 to 1 doesn't contain 0 or doesn't contain 1. There's no biggest number in this interval. There's no smallest number in the interval. 0 is not the smallest number because 0 is not in the interval. 0.1 is not the smallest number because you can go less than 0.1. 0.01 is not in the interval, not the smallest number because you can go less than 0.01. Is dx the smallest number in this interval? We're not going to go there. No infinitesimals right here. Okay, this is real math, not hyper-real math at the moment. Real numbers, not hyper-real numbers. Coming back here, this set D, this domain, is a closed set. It contains its boundary. Closed set contains all its boundary points. Points along the edge. What is the technical definition of a boundary point? What I'm talking about here is that near the beginning of chapter 12, actually. This is the section about limits, this terminology. What does it really mean to be on the boundary? It means if you take an open disk near the point, no matter how small, there's points both in the set and outside the set, inside that disk. Say it again. This point that I drew here, this dot, is on the boundary of the red set. Intuitively, the boundary there, that's the ellipse, is like a fence separating the set from the outside of the set. Technically speaking, that means no matter what disk I put around that point, no matter how small, there's points inside the set and outside the set that are in that little disk, no matter how small the little disk is. Those are the boundary points. And the set overall is closed because it contains its boundary points. On the other hand, a set inside the boundary is in the interior of the set. It's not a boundary point, which means there's at least one disk, in fact, infinitely many, if they're small enough, around that point that's completely inside the set. Are there open sets as well as closed sets? If we got rid of the boundary, the resulting set would be an open set, and every point would be an interior point. This has relevance, and what I'm talking about here is not completely irrelevant to optimization. I got to go quick here. You can optimize this function without calculus. How? Think about it. Yeah, just think about it. Thinking about this function over this domain, as you approach the boundary, what happens to it? The outputs get close to square root of 1 minus 1 because you're getting close to where this equals 1. The boundary, the ellipse. And in fact, along the boundary, along this ellipse, it equals 0. The output of the function is 0. So this function has a minimum value of 0 along the boundary. F has a minimum value of 0 along the boundary of D at all points along the boundary. In fact, you could say it's an absolute minimum, as the book does. I prefer the word global. I'm going to put both words there, global / absolute minimum value. It's as small as it can be, globally, absolutely. It's got a maximum value. Where's the biggest this could possibly be? Is square root of 1 is the maximum value, because if you're at the origin, if x and y are both 0, that makes this what you're subtracting as small as possible. You're subtracting 0. So the resulting thing, 1 minus that, is as big as possible. Square root is also as big as possible. F has a global / absolute maximum value of square root of 1, which is 1, at one point, x, y equals 0, 0. That it's got a global max and min value is guaranteed by a very important theorem called the extreme value theorem. I'm not going to write it out, but I want to emphasize that that guarantees F has a global max and min value over D. What does it say? It says if you've got a continuous function, if F is a nice continuous function, and the domain happens to be closed, meaning it's a set containing its boundary, and bounded, meaning it doesn't go off to infinity in some direction. By the way, you can have closed sets that do go off to infinity that are unbounded. For example, the entire upper half plane above the x-axis, including the x-axis. It includes its boundary, which is the x-axis, but it goes up forever and ever. It's unbounded. There's a distinction there between boundary and bounded. You want to make sure you understand the distinction. Boundary in that case is the x-axis. It's the edge, the fence of the domain. But it's not bounded because it goes up there forever. It's everything above the x-axis. This is a bounded set. It doesn't go off to infinity, off forever and ever in some direction. It's a bounded set. When you have a continuous function on a closed and bounded set, it's guaranteed to have a maximum and minimum value. In fact, global max and min. Ultimately, for your homework, though, you're mostly trying to find what are called local maxes and mins. This function also has a local max and min where it has global maxes and min. Global implies local. The book uses the word relative instead of local. I prefer the word local. But you'll see absolute and relative in the reading. I use global and local. Global implies local. So these things that are global maxes and mins are also local.